So one thing we can do here that's interesting is use this to calculate something like how fast a satellite would have to be going to orbit the Earth at some particular distance. And in fact, it's interesting. It turns out that you might not realize it at first, but we can show from this math that given a particular speed for a satellite orbiting the Earth, there's only one radius it can have to make a circular orbit. Now, if it's not making a circular orbit, that's different. But or vice versa, at a particular radius, if you want a circular orbit, a satellite has to be traveling at a particular speed. So how do we work this out? Well, we use what we just did, and we use the momentum principle. And it looks like this. So here's our orbit. Here's the momentum. Here's dp dt. There's the Earth. And you just said that there's the only non-zero component of dp dt is the perpendicular one. So we can write that piece of the momentum principle, dp dt perpendicular, is F net. It's equal to the component of the net force perpendicular to the momentum. Well, in this simple case, not dp dt is perpendicular to the momentum. The gravitational force is surely also perpendicular to the momentum since it's pointing. So there is no component of the gravitational force parallel to the momentum. And so this is just going to be equal to the gravitational force. So let's take magnitudes. We now took care of directions. So we have PV over the radius of the orbit is equal to the magnitude of minus g, mass of the Earth, mass of the satellite, over same r. So this is the radius of the kissing circle. But it's a circular orbit, so that's r squared, and we have an r hat here. And so satellites are not going near the speed of light, so gamma is nearly 1. So we can say this is mass of the satellite times v over r is equal to g, mass of the Earth, mass of the satellite over r squared. And some things can drop out here. We've got this on both sides, which makes it look like the mass of the satellite actually doesn't matter in this case. So we have magnitude of v squared is equal to g times the mass of the Earth over, we can cancel one of these r's, r. And so suppose we said, well, the satellite, we know the speed of the satellite is 8 times 10 to the third meters per second. What's the radius of its orbit if it's going in a circular orbit? Well, looks like we can solve for r is going to be g times the mass of the Earth over v squared. So we have 6.7 times 10 to the minus 11 Newton meters squared per kilogram squared. What's the mass of the Earth? 6 times 10 to the 24 kilograms. We decided it was going 8 times 10 to the third meters per second. And now we need to work it out, and we could find out what the radius of the orbit would be. Squared. Thank you. And what does that come out to anyway? I actually didn't write it down. Somebody got a calculator? 6.2 times 10 to the 6th meters. So about that's the radius. Yeah, that's the speed. That's pretty fast. Okay? So we can actually calculate things.